This session is Colin Cooper from King's College London, who's going to tell us about multiple agent random
Of course, the duality is what led them to discover it, but in
we have some order, please.
Yes, have some order, please. Okay, the first thing I need to do is explain the title, because what this actually is this must have been the last talk I gave on this, which was in my computer science department. This is multiple random walks on random R-regular graphs is what this boils down to, but the title might not give that impression. And this is actually a talk about the cover time in many ways, or the average time, or the hitting time of various properties of multiple agent or multiple random walks. So just to remind you what a cover time is, I always use this terminology that the vertex set is size n and the edge set is size m. If you start from a particular vertex, then the cover time from that vertex, CV, is the expected time for the walk to visit every vertex of the graph. And the cover time is just the max overall starting vertices of that quantity. Cover time's got quite a long history. It goes back to Alianos, Karp, Lipton, Lovash and Markov in 1979, which was about kind of maze walks and traversal sequences, and they proved that the cover time of any connected graph was less than or equal to 4 times the vertices times, sorry, 4 times the edges times the vertices, and
the year was not 79.
Oh well.
97. When was it? Not 97.
It's an old paper. It might be 73 or something, but it's, 79 is an upper bound, all right, on this. Anyway, in 1995, and I'm sure about that, Feiger proved upper and lower bounds on the cover time for any connected graph of n log n, which is basically the cover time on the complete graph, or 4 over 27 n cubed. And in computer science, cover time has an interest, because if you've got some large and unknown graph, I mean it's a large and unknown graph here because the rest of it's hidden off the page, then a random walk in that graph in order n cubed steps with with order log storage, you can search that graph and make a kind of a guess as to whether it's connected or not. This talk is basically, as I've already said, it's about several particles, several random walks going on the same graph, and we're talking about random regular graphs, regular of degree at least 3, and basically we consider 2 scenarios. The first one is what I call oblivious. This is too hard for me. Anyway, the first one I call oblivious. The particles do not interact. And the second one is interactive. The particles can interact. And the interaction model we use is that they can interact on vertices. So these 2 particles here are having a chat on a vertex, and they don't interact on edges. So if they pass on an edge, they just ignore each other. So that's the interaction model for the interactive case.
Excuse me, do
Yes.
they move simultaneously?
Yeah, they're independent random walks, right? Each particle is making an independent, simple random walk on the graph, and we're going to ask questions like, how long does it take to cover it with that, or we allow them to interact at vertices. Yes, so they move simultaneously. So you just think of it, apart from any interaction they make at a vertex, they're completely independent walks.
And when you say cover, it means that each vertex is hit by at least one of the particles.
Yeah, that's right. Well, I will define what I mean by cover time, if I can work out how to use this pointer. Okay, because this is on random regular graphs, basically the analysis is based on a previous result, which is that for random regular graphs of degree r, the cover time with high probability is this quantity r minus 1 over r minus 2 times n log n, where so basically it's between 2 n log n and n log n, depending on r. And because this parameter r minus 1 over r minus 2 turns up all over the place, we're going to give it a name. We're going to call it theta r. And So you need to remember that for future use. Okay, so just briefly to explain what the important parameter is in this analysis of that. The important parameter is a thing we call RV, which is the expected number of returns to a vertex in t steps, where t is defined in a way that suits our definition. So there you can see a picture of a walk starting at a vertex v. It returns to that vertex and then wanders off somewhere else in time t. And so Rt is the probability the walk starting at v returns to v at a particular step, and R sub t of z is the generating function of those returns on the first t steps. And what I call RV is that generating function evaluated at 1. So that's the basic parameter of interest which we need to, which we use to estimate these estimates in the future slides. Okay, so it's a bit of terminology. There's a walk u starting at a vertex u. Ft u arrows v is a first visit to the walk to the vertex v after the time t. So we don't really care. We're not asking what happens in the first t steps, big T this is, but we're interested in first visits after some time, capital T. And in what follows, we choose capital T to be a mixing time. And because these graphs are rapidly mixing, the walks aren't going to get very far in the first log or log squared steps. So, they don't visit many vertices anyway. So that's not a matter of great importance in these analyses. Okay, so this is basically the thing which the analysis is based on. You've got a mixing time, which is quite a good mixing time. So it's like 1 over n cubed from the stationary distribution. You've got a couple of conditions, one of which is rather technical. I don't understand why this doesn't work. It does work. Okay, so this is a technical condition. It says that over some circle, which is 1 plus 1 over the mixing time, the generating function is, or the absolute value of the generating function is at least some constant, right? And this is a circle in the complex plane. And the second one is just some simple conditions on the relationship between the mixing time squared and the stationary distribution of the vertex. It's got to be little o of 1, and we want the mixing time times the stationary distribution of any particular vertex to be at least 1 over n squared. So they're just conditions on the mixing time and the stationary distribution. And then if they hold, the probability of a first visit from u to v after the time, after the mixing time, is basically p of v over 1 plus p of v to the t plus 1 plus an error term, where this p of v is totally a function of the kind of geometry of the vertex. It's the stationary distribution of the vertex divided by the number of returns to the vertex during the mixing time. So it depends on the local graph structure of the vertex only and nothing else. So this is the kind of that's our first visit probability, and if you rephrase that, so we have this other quantity which we call A of v, which is the probability that the vertex is unvisited after the mixing time. So we don't really care if it's visited before the mixing time, because the walks can't visit much in that time. Then when you work that out, that basically has this formula here, which looks a bit messy. But when you simplify it, the probability it's unvisited after the mixing time is 1 minus the stationary distribution divided by the number of returns in the mixing time raised to the power of t plus error terms. So the waiting time to the first visit is approximately geometric, with a success probability which is the stationary distribution divided by the number of returns in the mixing time. So if it's geometric, the expected wait time is 1 over the success probability. So the expected wait time is, the expected time for the first success is the number of returns in the mixing time divided by the stationary distribution. And that is, that's true for any discrete Markov process which satisfies the conditions of that lemma. But it's got to be a Godic Markov process, which satisfies the conditions of that lemma. So that's just a general lemma which is useful in all sorts of cases, but we basically kind of see how much we can get out of this in the situation of walking on R regular random R regular graphs. So this is an application of that lemma to a particular problem. Okay, and for random R regular graphs, you can work out R of V for most vertices because they are tree-like. So that means that essentially up to some distance, if the particle's walking, this is a start vertex here, if the particle's walking away from that, then at any stage the probability it goes back towards it is 1 over R, and the probability it goes away from it is R minus 1 over R. So basically it's the same up to a certain point as a random walk on the line with a drift away of R minus 1 over R. And the expected number of returns to the origin before it wanders quite a long way off is R minus 1 over R minus 2 for that problem. And then there's a kind of second order error term for what happens, you know, in the sort of in the last bit before the mixing time t. So that's where that thing comes from in the original thing for our regular graphs. And that's the theta r again there. Okay, so the first part of the talk is multiple particle random walks. The particles are oblivious, so to answer Svance's question, they're all walking around independently and not taking any notice of each other whatsoever. And the question we want to ask is, what is the cover time when you've got more than one particle? So there's a picture of it, two particles wandering about. One of them's wandered over some bit of that earlier on. They can cross over, do what they like. It's completely irrelevant because you know, they're just walking independently. And there's a definition of the k particle cover time. They've got k particles. We've got V1 up to Vk are start vertices. We don't really care what they are because it doesn't make any difference to our analysis here. And the cover time of the graph with k particles is the maximum over all start vertices of the expected time to visit everybody, you know, depending on where you start. And there's a thing which we call the speed up, which is basically the cover time with one particle divided by the cover time with k particles. And this value of speed up was studied by Alon, Avin, Cucci, Cosma, Lotka, and Tuttle. And I haven't put the date there because I don't know what it is, right? And they found that for expanders, the speed up was omega k for k less than n particles. And so our first kind of question was, what's the precise value for random R regular graphs? That was our first question we asked ourselves. Okay, so the result for random R regular graphs is that if R is greater than or equal to 3, with that parameter theta r as before, and we choose a graph randomly from the set of R regular graphs, and for k equals little of n over log squared n particles, the cover time is basically the cover time for one particle divided by k. So the speed up is exactly linear, and it's independent of the starting position of the particles, and it serves as an upper bound for larger values of k. So certainly in the case of that particular sparse expander, the speed up is precisely linear. And the proof is like a one-line proof, really, because we already had that for one particle, the probability after the mixing time that it wasn't visited was 1 minus that thing to the power of t. So if you're letting k particles all have a go independently, you're raising that to the power of t. And then you just have to make some small calculations about what happened during the mixing time. Basically, you have to show that at some time slightly less than this, there is a large set of unvisited vertices. So, you know, and it's larger than everything that could have been visited in the mixing time. So there's stuff which wasn't visited irrespective of what happened in the mixing time. And that suffices to establish that result. Okay, so now we move on to multiple agent random walks where the agents, i.e. the particles, are allowed to interact in some sort of way. And they're only allowed to interact on vertices. Okay, so they're all making independent walks, but when they get to a vertex, they can do things to each other, basically. And the kind of things they can do to each other, well, there's all sorts of things they can do, but we decided on two particular examples, the first of which is they can have a chat. They're talkative particles. So, I mean, this is where the word agents gets dragged in, because this is about broadcasting, yeah, between the particles where they talk to each other. The second thing is they could be predatorial. The writing's not too clear, but that's the word predatorial. That's one type of particle. That's another type of particle. The predatorial type particle eats the non-predatorial type particle. So, in that case, there are K predators and L prey, and that should actually say L minus 1 there. So the predators stay at K and the prey go down to L minus 1. Another thing they can do, which is basically just predator-prey, is they can kind of stick together, so when they see their mates, they can all wander off, in a group somewhere happily. So when they meet, the number of active particles goes down from K to K minus 1. And the last thing they can do is they can kind of see each other, and it's like driving in London, they can drive into each other, and then the number of particles goes down from K to K minus 2. So these are just sort of regimes, let's see. Try a few things and see if we can work out what's going on. Okay, now in this case, I said for the cover time, it didn't matter where the particles started because nothing went on during the mixing time. For this case, you actually have to be a bit stricter about where they start, because if they all start on the same place and they're going to drive into each other, they've all driven into each other at time 0. So we don't want that. So we need something which we call general position, which is not too close. So 1 to 4 edges away is not general position. We need something probably slightly further away than that. Okay, so for a pair of particles, basically just let's look at a pair of particles first of all. So mu of v is the number of steps before the two random walks starting at vertices u and v first meet. So it's a random variable, and if u is equal to v, then it's 0. So we need to insist that the starting positions of the particles are not too close. So we say that k particles are in general position if the starting positions satisfy that for each of them, the distance between them is at least log n or log k. So if k is less than log n, then basically we say log n is far enough away to sort of be in general position. Otherwise, we like them slightly further apart, because we're going to repeat this process over and over again when these things are eating each other. So we need, when two of them meet, we need the rest of them still to be in general position with high probability, so that they don't do anything in the mixing time as it remixes. Okay, so that's all the legal stuff. Okay, so if you've got k of these things starting off and they start off in general position, then basically the expected time before there's at least one meeting between some pair of particles. In other words, somebody meets somebody is basically 1 over k choose 2, because that's the number of particle interactions, times theta rn. Well, theta rn is the kind of it's the expected hitting time of a vertex by a single random walk, basically, in the single random walk regime. And just again, we remind what theta is. So it's basically this thing is the same. That was the expected hitting time of vertex, and it's just 1 over k choose 2. Because the pairwise interactions will dominate. In order to do this, I need to basically explain a little trick you can do with this technique with that first visit time lemma. If you've got a thing and you want to ask a question, not the first time that vertex B is visited, but the first time that some vertex in a set is visited, then basically you can kind of shrink those two vertices together, and we call gamma s the shrunk vertex of the set. So we take the set and we just shrink it into a vertex. Gamma g is the graph G shrunk with that vertex shrunk. Everybody else has got the same degrees, and this has got the total degree of all the shrunk vertices. then providing the thing is mixed or reasonably mixed, the probability that it's unvisited after time capital T for the set is about the same, is asymptotically the same as the probability that it's unvisited in the shrunk set, in the shrunk graph. So basically you can deal with sets by shrinking them to single vertices, and that's useful in the cover time proof of a single random walk, because if the vertices are far apart, then you can use that to prove the probability that one's unvisited and that one's unvisited is approximately independent, because there are no short paths between them if they're far apart. So it helps in that. It came from the original cover time analysis, this technique, and it's clearly very useful when we're dealing with multiple particle walks, because here's a particle scooting around here going from 1 to 3, and here's one going from 2 to 3 the other way, and if we take the two things and stick them together and sort of put the edges in corresponding to possible things, so there's 1, 3, 2, 3, that's the pair of walks there, then this diagonal is places where the walks coincide, and we can treat this thing as one single random walk on k copies of this thing, or in this case 2 copies of the graph, and we then just shrink this diagonal, as we call it here, down to a single vertex and analyze the multiple walk in the graph with the shrunk vertex. So this is how we're going to say all these things about cars in London driving into each other. Okay, so how do we find the probability that nobody is met by time t after the mixing time? We basically take k copies of the graph. We make k random walks on the original graph, 1 random walk on the k copy. We have a set which is the set of vertices with at least 2 vertices the same. A median between particles is a visit of that walk to that set. We coalesce that to a single vertex. We estimate the returns to that vertex within the mixing time on the coalesced graph, which is going to that's got a rather longer mixing time, or our estimate of it is not so good, so that's going to make our estimates poor for some things, for large numbers of particles. And it's all the same as usual. The probability that the set is not visited by step t is basically 1 minus pk to the power of t, where pk is the stationary distribution of the set divided by the number of returns to the set during the mixing time on the coalesced graph, and we just plug it into the problem. So before we do that, we've got to estimate all the things. That's what we're trying to deal with. The thing is that over that. That's quite easy to estimate. It's approximately k choose 2 over n, the degree of the vertex. You can prove that basically the number of returns to the vertex during the mixing time is the same as it was for a single walk, more or less, and there's a reason for that. So this thing is that thing there. And the reason why it's that is most of the meetings are between pairs of walks, and we can calculate the expected number of re-meetings between pairs of walks in the underlying graph. That's not too hard to do. The only problem is that the mixing time is rather long, so that we have to take quite a lot of care to make sure that they don't re-meet during this long time, which means that our results will only be for some n to the small constant only. We won't be able to do it right up to n because of this poor mixing time we've got here, which is basically the mixing time in the underlying graph multiplied by the number, n to the something. Yeah, so it's an order n mixing time, but it's n to the little o. It's n to the alpha for some alpha less than 1. Okay, so basically we can just do the same thing as we did with the other one, and we can get the unvisit times, and they're geometric, and we either have for all particles which are all the same, basically we have a k choose 2 there, whereas if we've got predator and prey, then we've got s of one type of particle and k of the other. So basically just the parameters differ, and so if it's k particles which are all the same, the first re-meeting time is 1 over pk, which is given by that, and if the particles are of 2 types, the first re-meeting time is 1 over qk. So we can get the expected re-meeting times, and everything by using this general position. it will be the case that mainly the other particles won't have met during that meeting time when they meet, and so we can, and they won't meet again during the mixing time, so we can do this over and over again with a diminishing number of particles and get, a sensible set of expectations for the expectation of the sum, because they're still valid, the results. So here's the first result, which is predator-prey, which is the big particles eating the little particles. And there are k big particles and l little particles, and both of them are less than n to the 0.01 or something. And they're walking randomly. And the only interaction is when they meet on a vertex, the big ones gobble up the little ones, because that's what predator-prey do. So the expected extinction time of the prey is basically the theta Rn, the original thing, the nth harmonic number, which is the number of prey, divided by the number of predators. So you can work out how long it takes for everybody to get killed off. Okay, and two applications of that are when all the people sort of wander around sticking together with their mates, then the expecting time for everybody to stick together, irrespective almost of how many people there were originally, is twice the expected time for a random walk to visit, an arbitrary vertex. It's twice the expected hitting time. And if it's drivers in London, then you actually get an extra log 2 in there as well. Presumably it kind of thins out rather more quickly at some point. So there are two kind of applications of that thing. I mean, I know this is just messing about, but it's nice to see that you can do some things. And this is the kind of, this is the original problem which the kind of the computer science people in my department wanted to know about, which is broadcasting. The model is as follows. Somebody's got a message, and the message is basically, well, it's gone, but the message is that if you want to go to the conference tonight, then you have to be outside here at 7 o'clock. And, you will pass that on to your friends when you see them. So that's the message. And basically, when anybody meets, they have a chat. So they pass the message on, they're outside the Newton Institute at 7 o'clock. And so that's the broadcasting model. So the broadcasting time is 2 times theta Rn, where theta Rn is the hitting time of a single random walk, times the k minus 1th harmonic number divided by k. So as k tends to infinity, the expected broadcasting time is basically some constant times n log k over k for k particles, where k goes up to n to the the 0.1 or the 0.2 or something, or 0.01. And you can make a comparison with this between indirect and direct broadcasting between the particles, because as we said on the previous page, if there's a lot of particles, then the broadcast time is basically n log k over k, and single broadcasting is basically one predator and k minus 1 prey. Right? I go around and I tell you individually that you've got to meet here at 7 o'clock, and then I eat you, or whatever. So it doesn't matter what I eat you or not, because afterwards I'm not going to tell you again. I only have to tell you once. So for single broadcasting, the time it takes is n log k. So the speed up of multiple broadcasting over single broadcasting, the expected speed up is k over 2 for a large number of particles. So that's, it's a kind of linear speed up if you allow each other to tell each other that that's where we're going tonight and at what time. And that's the end of the talk, actually. Thank you.
Questions?
Can you say again what assumptions you have on the graph?
Yeah, they're okay. Well, they're random R regular graphs. Basically, they're not bipartite, and there's probably that most of the vertices are tree-like up to some sort of log n distance from a vertex. Yeah. Because we use that to calculate that R of v for tree-like vertices. That theta minus 1 over theta minus 2 is only an upper bound if it's got cycles in it, because it alters that thing. So the basic assumption is that, yeah. and there's not too many cycles. There's little over end cycles. There's various sort of not too many cycles, and it's not bipartite, and that's about it actually. Yeah. Oh, and we use the fact that the second eigenvalue is at least 1 minus epsilon for some some constant epsilon. You had to get a fast mixing time rather than working out the conductance. So, but you need some sort of some sort of expansion property. Yeah.
So
The chair is supposed to be picking these people out. Who was the second?
No, you pick.
Okay. Well, in any order then, yeah. A random agent.
There's one. So,
I'm Elena, yeah.
okay, so sometimes we are interested, especially in computer science, not to cover the entire graph,
Yeah.
but a constant fraction.
Yeah.
So I
Yeah.
presume these methods go through, right?
Yeah. Yeah. I mean, you
It's
can
by-
work.
by nature.
Yeah. You can work out, what a constant fraction is, and etc. Yeah.
So that would be like theta r n.
But
Or times whatever you need for the constant.
yeah, well, there'll be some.
And then-
I mean, theta rn is just the hitting time of a random vertex. Yeah. So I mean, it would
so
be
each
whatever.
code goes through.
I mean, you'd decide how many vertices you want to visit, and then you'd work out, the probability they're all visited within a certain time. So you'd find a time in which, bounded above, they were visited. Then you'd have to prove there were some which, were hanging about till almost that time. Yeah, I think you could do that. Yeah. No. Yeah.
So one, if topology, you were correct about the 79.
Yeah. Yeah.
Second,
You looked it up. Yeah. Okay.
second is the coalescence time when of these. If you start, say, one particle at each vertex of the graph, then I think there's still a possibility that the coalescence time is for any graph is bounded by the maximal hitting time.
Yeah. Is that right? I mean,
Up to constant. I
yeah.
think that's an open question. So first you established it in stronger form for these graphs, but I think this is still an open problem for
So this is start one particle at each vertex.
right and
Yeah.
do lazy random walks
Okay.
or continuous time random walks.
Until they all get together. Till the whole lot get
Continuous
together.
time random walks and you wait and two particles coalesce. You meet like. So is it true that that in complete generality, a constant times the maximal hitting time of everyone? I think it's known up to a log n. But
Conjecture of Aldous, yeah?
what? That's it. Right.
That's not for regular graph.
We-
In the book. Aldous.
You could get the distribution. I mean, you could take a pair of particles. I mean, and work it out for that, and then you could probably find a large deviation on that, which was good enough to sort of say they all.
Right, and that loses the factor of log n.
Yeah.
It's open whether you need to lose it.
Yeah, I don't know.
Last question is, where did you get that great picture?
Oh, that. I just. It's probably yours. I don't. Is it? It's from your. It's from your website. Yeah. I got it from your website. Yes. Yeah, it is great. Yeah. Yes. Okay. Thank you very much. I love it. Yeah. Mike.
You had two kinds of problems. One was covering, the agents just getting to...
Yeah, they're just wandering about, yeah.
And then a different kind of problem, the conversation where they were trying to pass the message to all the other agents. Presumably, if you look at distributing an initial message to all the sites, then that can be handled with the same sorts of techniques.
Yeah, I guess so. Yeah, I mean, so what
you didn't cover that directly.
I mean, how are you distributing it? Initially, somebody's got it.
Contagion. When two agents meet, they pass the contagion on, and you want to know how long before all the states get contaminated.
So I guess that would be the cover time then, because.
Well, they can't. It's not the cover time because an agent has to get infected before it.
Oh yeah, that's true, isn't it? Yeah. No, okay, I don't know then. Interesting question. Yeah, all right. So next time round, it'll have.
Oh, you want more positive, spreading the good news from X to gold.
Hang on, let's just get back and see what the.
But what was the time? But isn't the time until they all have met each other proportional to n, and then the cover time is like n log n?
Yeah, that's.
It will be dominated by the cover time.
Yeah, it will, because you've got that's the time for them all to get contaminated, right? And it takes n log n over k for them to cover everything. Yeah. So it should be, they're still, by the time they've got contaminated, they haven't seen much of anything really.
Yeah, but they're all clamped together perhaps at that point.
Oh, well, you're letting them. I thought you were just broadcasting.
No, just broadcasting.
Yeah. You want them to stick together. You want them to stick together, and no, I think for broadcasting it's just the cover time. Yeah, that was because you've got the log n as opposed to log k, and this is. This doesn't go up to k equals. Well, it depends really what the. Okay, if k is little o of n, then it's the cover time. Yeah. At a certain point, log of k, is sort of like alpha log n, yeah.
Another question?
So, is the cover time concentrated at its mean? Or not?
Yeah, for a single agent, yes.
Yes, but if you have several agents.
Yeah, I think so, probably up to a certain point, because slightly above that cover time, all the vertices have been covered with high probability, because it's just, whatever it was raised to the power of k, yeah? So, I mean, for a single agent, okay, let's just do it for a single agent first. For a single agent, it was concentrated. It was a with high probability result, yeah? Okay, so it's still, the upper bound is still with high probability, and basically you're just going to find the same set of vertices which haven't been visited by anybody at a time slightly less, yeah? Except the time when they haven't been visited has gone down from whatever it was to whatever it was over k, yeah? So yeah, it's still concentrated, yeah.
When you say high probability, what do you mean?
Well, I mean, with probability, the error term is sort of like little o of 1 in n, yeah, the number of vertices, yeah.
Any more questions? So can we thank Colin again?